Good morning, everyone. Myself, I am U Saraswati, studying MTech third year, third semester in IRA Institute of Technology and My Tech Talk topic is about privacy applications in quantum computing, which is going to be in the subject of quantum computing. Privacy applications in quantum cryptography. Introductions to privacy amplification. First of all, we have to know about what is privacy amplification. Privacy amplification is a crucial process in quantum cryptography aimed at reducing and eavesdropping knowledge of secret key. It enhances the security of quantum key distribution protocols by distilling a short, more secure key from partially composed key. Mainly, the cryptography process is about sharing the keys between the sender and the receiver while communicating both between two users. They maintain two keys, that is public key and the private key, and it enhances the amplification will enhance the security of quantum key distribution protocols by distilling a shorter secure key from partially compromised one. This process ensures the resulting key is nearly identical for both parties even in the presence of an adversary. It is a secure process. Next, coming to what basics of quantum cryptography. Quantum cryptography leverages principles of quantum mechanics to secure communication channel. The most well-known protocol, the protocol that is used in quantum cryptography is BB84, which allows two parties to generate a secret key that is shared between two parties with security guaranteed by quantum physics. Security in quantum key distribution relies on detecting any eavesdropping which inevitably distributes the quantum states being transmitted. First of all, what is about eavesdropping? Eavesdropping means while they are sharing the information between two parties, they maintain the key, and this key is scanned by the some third person, and this process and knows everything information about the keys. This is about eavesdropping. Next, threat model and eavesdropping, and the two models that we are going to be used in quantum cryptography is threat model and eavesdropping. And eavesdropping, commonly known as eve, many attempts to gain information about the key during transmission. The unauthorized person makes many attempts to gain the information about these keys that are going to shared by the two legitimate users. Quantum no-cloning theory prevents perfect copying unknown quantum states, but partial information can still obtain. Privacy amplification is used to mitigate the information Eve might have gained, ensuring the key remain secure. By using this eavesdropping, some privacy amplification is used to overcome this eavesdropping so that the key remains secured. Need for privacy amplification. The main reason that we are going to be used this amplification in quantum cryptography is after quantum transmission, the raw key may contain some information leaked to the eavesdropper. After quantum transmission, after transmitting the information between these two parties, some information the third party will will collapse this security and grab the information by the eavesdropper. Classical error correction is performed first to reconcile difference between legitimate parties keys. Some error corrections, we have to do some corrections to know whether the sending party, the two parties are legitimate users or not. Privacy amplification further reduces Eve's knowledge, resulting in high secure. And by using this amplification, the eavesdropper knowledge, uh, the eavesdropper is unable to ga- gather the information about the key, so the communication is well secured. By this quantum cryptography, we can communicate the information, and we can send the messages over all the world. Next, concept of privacy amplification. The main concept that we are going to be used in privacy amplification involves applying a hash function to partially secure key to produce shorter, more secure hash function. Already we know that hash function, the first come with the first serve. It works on the FIFO, and privacy amplification mainly uses this function for to more, not for more secure for the keys, but it provides only the partial security for the keys. The process exploits the fact that eavesdropper information is limited, allowing the legitimate parties to discard the vulnerable parts. The process exploits the facts of eavesdropper information. Universal hash functions are typically used for their security properties. Mathematical foundation. Privacy amplification is grounded in information theory, especially the concept of min entropy. The leftover hash lemma produces a bound on the amount of secure key that can be extracted. The amount of compression depends on estimated amount of information leaked to Eve during transmission. How to implement this privacy application? Practically, privacy amplification uses universal hashing function such as Toeplitz matrices, Toeplitz based hash functions. The hash functions may also contain some NAND gates, NOR gates, exclusive OR gates, and it also uses the algorithms that we are going to process the computational problems. The parties agree on the hash function publicly, then apply to their shared key to produce final secret. By using these functions, both the parties will create one public key, and by using this public key, they create their own private key for secure purpose. The process is computationally efficient and can be implemented with standard cryptographic algorithms. Security guarantees and assumptions. How this privacy amplification provides security guarantee. Privacy amplification guarantees that final key is nearly indistinguishable from a uniform random key to eavesdropper. It is security depends on accurate estimation of the Eve's potential information and the properties that we are going to be used in hash function. Assumptions. These assumptions include some classical communication channel. Mm, Here we are going to be assume that they are the communication channels and accurate error rate estimation in quantum channel. Practical challenges and consideration. Coming to these challenges that are faced by the privacy amplifications, and some considerations are: accurate estimation of the eavesdropper's information is critical to determine the privacy amplification needed. So the main challenges that amplification is facing is that it is unable to accurately estimate the how the eavesdropper will gather the information about the keys. Finite key effects can complicate the process, requiring a careful statistical analysis. Finite key, that is a private key that is going to be generated by the sender, is requires some security, more security. So it is a complicated process. It should be carefully statistically analyzed. Efficient implementation is essential for real world quantum communication systems, especially over long distance. The communication that is took place over real world communications over long distance is difficult. Conclusions and future directions that we are going to improve in privacy amplification is: privacy amplification is vital, and it is a unique for ensuring unconditional security of quantum key distribution. Advances in hash function and finite key analysis continue to improve the efficiency and security of quantum key distribution. Some advancement should be made in the hash functions and some quantum key distribution system. Future research. Future research, it is mainly focused on integrating the privacy amplification with emerging quantum network architecture and protocols. Thank you.